So we are looking at minimum cost spanning trees and weighted graphs, and we said there are two natural strategies which are exemplified by two standard algorithms. So the first one is Prim's algorithm. So we have a weighted graph, so a graph with a weight function which assigns a number to every edge, and let us assume that the graph is connected, because otherwise if it's not connected to begin with, we cannot superimpose a tree on it. What we want is a spanning tree, a tree which is a subset of the edges which connects the graph, and if there are not enough edges to connect the graph to begin with, we don't even have a starting point. So assuming the graph is connected and it has weights, we want to find a minimum cost spanning tree which connects all the vertices in V. So the strategy that we are going to adopt is to incrementally grow it. So we start with the smallest edge, right, and we will keep growing the tree by adding the smallest edge that we can to the current tree while retaining a tree. So let's look at this example that we saw before. Okay. So supposing we start with the smallest edge. So the smallest edge is the edge between 1 and 3. Now we want to grow this tree. So the smallest edge with which, so we need to grow it, meaning we have to choose an edge which will extend this tree. So we can't choose, for instance, this edge right now, because this edge is not connected to the tree. That is the smallest edge overall, but it's not connected to the tree. I want to grow the tree. So I can take any one of the edges coming out of here, but not that one. So that one is out. I cannot do that one. Right? So I can take any one of the edges which is leaving the tree and extend it. So I take the smallest among those, which is 0 to 1. And so now I have a tree which has two edges, 1 to 3 and 0 to 1. Now I can take any edge which is leaving this tree. So the smallest among them is this edge with weight 18. But unfortunately, when I add this edge with weight 18, I create a cycle, right? And this is not a tree. So I cannot do this. So I have to throw this away and I have to go to the next one. So I go to the next one, which is that 20. And now I have a tree which connects 4 of the 5 vertices. And now finally, because I have reached 2, I am now allowed to add this edge, because now this edge is connected to the tree that I have constructed so far. So now I add that edge and I will get this tree, which if you remember, we had said last time that this tree has weight 44, and you can check that we've actually found that one. Okay. So this is Prim's algorithm. So formally, what Prim's algorithm does is it incrementally builds a minimum cost spanning tree. So it keeps track of a set of vertices which have been added, and it keeps track of a set of edges which have been added, because just because a vertex has been added doesn't mean that all the edges between them have been added. So if you look at the previous one, for instance, when we have added 3 and 0, it doesn't mean that the edge 0, 3 is added. So we have to separately note which edges belong to the tree. It's not just enough to say, it's not like Dijkstra's algorithm where we say we have burnt these vertices, so we are done with them. We need to know which of the edges were used in order to construct the tree. Right? So we keep track of these two things separately, TV, the tree vertices, and TE, the tree edges. So initially everything is empty. The way we described it, we will start with the smallest edge. So overall we look at all the edges in the graph and we pick the smallest edge. Okay? That edge, let it be from I to j. So once I do that, then I've started with a minimum tree, right? A tree consisting of just one edge. So the TV, the vertices in the tree are I and j, and the edge is this edge E which I just added, which is from I to j. Right? And now what I will do at each step is I will take an edge which starts in T and goes out of T. Right? So that's the reason we could not introduce, when we had this graph already drawn, right? The reason we could not choose this edge is because both endpoints are already in the tree that we have constructed. So we need an edge like this or like this, which starts in the tree and ends outside the tree. So we choose a minimum weight edge such that U belongs to the tree and the outside, the other edge, endpoint of the edge belongs to the other set. It's not in the tree. Among all these edges which are starting from the tree and going out, you take the smallest one and add it. Once you add it, you have added a new vertex to the tree. So TV gets expanded to add V in it, and TE gets expanded to add this new edge. So this is the algorithm for Prim. So again, going back to that example, so this is how we start. We start with both sets empty, right? And now we take the smallest edge overall, which is this one. This is how we start the algorithm, right? So when we start the algorithm, we say that 1 and 3 form my tree. So the tree vertex set TV has 1 and 3, and the edge set consists of the edge 1, 3. Now I look at the smallest vertex which has one endpoint in TV and the other endpoint outside, and it turns out to be the edge 0, 1. So I add 0 to TV and I add 0, 1 or 1, 0 because I am drawing it from 1 to 0 to this edge set. Okay. Now I cannot do 18 because it's not inside. So the next edge that I can do is 1, 2, because I need to find an edge which is inside to outside. So this edge is not allowed, right, because I have this condition that u, say for example 0 must be in the tree vertex set and 3 must be outside, but both 0 and 3 are inside. So I have to drop that edge. So I can only look at edges which leave the tree and go out. So among those 1, 2 is the next one. So I get 2 now in my tree set, and my tree edge set has 1, 2. And finally from here, I can get 8, you use that edge with weight 8 and get 4 into my edge set, in my vertex set, and 2, 4 in my edge set. So now I've got all, so I did this n minus 1 times, that's the important thing to do. So I basically started with 1, 3 and I did 1, 2, 3 times, okay. So I did this n minus 2 times, So I had 5 vertices, I already started with 2 vertices, so I have n minus 2 vertices to go. Every time I do add an edge, I add one more vertex into my set. So after I do it n minus 2 times, my vertex set has covered all the vertices. Remember, we have to assume that the graph is connected, otherwise it's not going to work, right? They will not be able to connect it. So this seems a little bit, I mean, on one side it seems reasonable, on the other side one might ask, why is this going to work? I mean, why does this particular strategy actually give me guaranteed the shortest, smallest tree overall, right? So to do this, let's prove some small graph theory fact called the minimum separator lemma. So what this says is that supposing I take my graph, right, and I partition it means I divide the vertices into 2 sets, u and w, right, and now I look at all the edges which have endpoints on opposite sides of this, right. So there will be some E1, there might be some other edge E2 and so on. There might be multiple edges which go across this partition. So they have one endpoint in U, the other endpoint in W, right. So among them, let's assume that we pick one which is smallest, right. So let's just for the moment assume that all of them have different weights. So we will see what to do with they have equal weights later on, but let's assume that the smallest one. So supposing one of these is actually smallest, so maybe this is the smallest one. Then what this lemma says is that no matter how I construct an MCST on this graph, that particular edge E3 has to be in my MCST. Okay. So the intuition is that somewhere in my graph I will be separating u from, in my tree I will be separating u from w, and the best way to connect u to w is via E3. So I must use E3 in my MCST, right. So this is the claim. So let's see why this is true, right. So as I said, let's assume for now that all the edge weights in our graph are actually different from each other. Okay, so it just simplifies the argument a little bit. So this is the situation we are looking at, right. So we have a tree, and then this says for every partition, right. So this is a universal property. It says no matter how I partition my thing as u and w, this property must hold. So let me just assume this is some arbitrary partition of my graph, right. So I have split my vertices into 2 sets which are disjoint, which together cover all. So partition means exactly that, partition, right. If I partition my toys with my sister, then I have to take some and she has to take some, and both of us get one or the other toy, and nobody gets left, no toy gets left out, right. So partition just means that the 2 sets are disjoint and the union is the full set. So that's what a partition is. So u and w together cover all the vertices and there is no overlap. So now the question is that supposing I have a tree and I look at this graph, this edge which I am promised must be in the tree, right. It says that the smallest edge which connects a vertex in u to a vertex in w, right, the smallest edge connecting these partitions must be in my tree. So supposing it is not in my tree, right. So I am assuming, for the sake of contradiction, that I have built a tree which excludes this vertex which the lemma promises me should be in my tree. Now on the other hand, I have built a tree, right. So this hypothetically, this capital T is an MCST. It is a tree, it is a connected graph on the underlying vertices. So there is no problem going from u to w, the small u to small w. There must be a path, right, because it's connected. So this path starts in the left partition and it ends in the right partition, right. So imagine that this was a river separating 2 sides of the city. You cannot go from this side to that side without crossing the river, right. So I am not using this edge E which I want, but I have to cross somewhere. So there must be some other edge, let me call it F, where this path crosses, right. You cannot go from the left side, from the red set to the purple set, from capital U to capital W, without crossing from this side to that side via some edge. And if I assume that I have not taken the edge E which I am interested in, which is the smallest edge connecting U to W, I must have taken some other edge, right. So this is what the picture looks like. So now we can see what happens, right. So this is connected. So now supposing I drop this edge and instead keep this edge, then I claim that everything that was connected before is still connected, right? Anything that I can reach, I can now go from there and reach, right? So anything that I can reach by following this u to w edge, I have this long path which goes via u, w and comes back to w prime, and I can do it. So therefore the connectivity doesn't change, but I have replaced f by a smaller edge, right? So therefore if I replace f by e, I have got a smaller or a cheaper spanning tree in terms of cost, right? So this contradicts the assumption that I started out with a minimum cost spanning tree. I started off with an MCST and I have told you how to get a smaller one, so therefore this could not have been the case, right? So either T was not an MCST or T was an MCST, but this assumption that E did not belong is false. So therefore we have established through this contradiction this lemma that says that if I take any partition of a vertex set and I find the smallest edge going back and forth across that partition, that must belong to every MCST that you build. So if you choose that edge, you're okay. If you don't choose that edge, you're in trouble. So just let's dispose of this case of distinct edge weights before we look at Prim's algorithm, right? So what if two edges have the same weight? It's not a big problem because you just need to have a strategy to choose one or the other. So you need to arbitrarily decide that one is smaller than the other in order to make this thing work. Which one will go into every tree? So if you fix a strategy, so to fix a strategy, basically you assume that you have numbered the vertices in some fixed way from 0 to m minus 1, and then you just decide that the ordering is such that either an edge, so this is the numbering, right? So E with number I and F with number j. Now so suppose E and F are two edges, I would have assigned each of them a number, a different number between 0 and m minus 1. So I look at now E comma I and F comma j, and if the weight of E is smaller than the weight of j, I declare that this edge is smaller. But if they have equal weight, then I will look at the index and I will say if the index I is smaller than the index j, then E comma I is smaller than F comma j. So this gives me a way of kind of ordering all the equal vertices. So then my lemma will say that it must include the smallest in terms of their ordering, right? So that's what we say. So it's not a big deal, so it can be done. So this lemma holds in general even if the graph has weights which repeat. So now what is the impact of this lemma on Prim's algorithm? So in Prim's algorithm, right, what we have at any given point is the set of vertices which are in the tree. So if I look at the set of vertices which are in the tree and the set of vertices which are not in the tree, let me call it W. So this is the set minus operation. So V minus TV, right? So I used it there also. So this means all the elements which I get by removing the elements of TV from V, right? So W and TV together have all the vertices and they are disjoint, so it's a partition. Okay. So therefore now if I look at what Prim's algorithm does, it says I am currently looking at a tree which I have built and I am looking at all the edges which go out, which connect my current tree to vertices which are not in the tree, and I pick the smallest one. But that's nothing but this minimum separator, right? For this particular partition, I am picking the smallest one, right? So therefore the one that I am picking has to belong to, so I am not picking anything wrong. So every edge that Prim's algorithm picks is guaranteed to belong to every MCST by this lemma, right? And since it does that and it picks exactly n minus 1 edges overall, all the edges are necessary and therefore they all are part of an MCST, right? So that's the correctness argument. So in fact, there is a slightly stronger statement we can make. If we look at a vertex V, right, and we look at everything else, the whole set minus V, then if I look at the vertices, the edges coming out of V, they connect the vertex V to its neighbors and all those neighbors belong to the other partition, right? So by this lemma, among those edges which are coming out of a vertex, all of them are connecting the partition containing V alone to the remaining things. The smallest edge leaving a vertex is this minimum separator. The minimum separator separating V alone from everything else, and by this lemma that smallest edge must belong to every MCST. So basically if I start at a vertex and I look at all the edges which are connected to it and I pick the smallest one, then that smallest one is guaranteed to be in every spanning tree, every minimum cost spanning tree. So actually therefore it doesn't really matter that Prim's algorithm started with this minimum cost edge, okay, that is a bonus. The minimum cost edge is of course going to be the minimum separator between the partition of the two endpoints, so that is fine. But you can start anywhere, right? So you can start with any vertex, and we know that from that vertex the smallest edge leaving it is a minimum cost separator between it and the rest. So I can start with the vertex TV set to be just a single vertex and no edges, and then I can apply Prim's algorithm. What Prim's algorithm will first discover is the smallest edge which connects V to one of its neighbors, right? So that will be my first edge, and so on. So Prim's algorithm will work from any starting point. The first iteration will pick the minimum cost edge leaving V, which by this lemma is correct, right? So Prim's algorithm is a natural way to build a minimum cost spanning tree starting at any vertex, as we saw. Okay, so the way we first presented it was starting with the minimum cost edge, but starting at any vertex you can build an MCST because of this minimum separator lemma. So at each edge what you do is you take the tree you have already constructed and we pick the minimum edge connecting that tree to the rest. So we extend the tree one edge at a time, and at each point, because we are going from inside to outside, the new edge is guaranteed to keep it a tree, and finally every edge that we get is guaranteed to be required by the minimum separator lemma. So every edge that we add was required to be in the tree, and therefore overall we have added no useless edges, so we must have got a minimum cost spanning tree.